So let's talk volumes and capacities. Now, imagine that this is your lung. Okay, this is just a lung. Now, do you use the entire volume of your lung when you breathe? Obviously, no. Right? So, the volume that you use for your tidal respiration, normal breathing, when you're not like trying to excessively bring as much as you can or get as much as you can out, it's called tidal volume. Okay? Now, think about yourself now. Can you inhale more air compared to what you are inhaling now? Yeah, absolutely. So that extra volume that you can get in here is called inspiratory reserve volume. Okay? Good? Good. Now, next. Can you exhale a little bit more compared to what you're exhaling normally now? Yeah. You get everything out. So that extra air that you can exhale in addition to your tidal volume is called expiratory reserve volume. Now you notice that it doesn't go all the way to the bottom. There is some air in your lungs all the time. This is called residual volume. Okay? Because you can't deflate your lungs for them to not have any gas whatsoever. Are we clear? Now, those are 4 volumes. Any questions about the volumes? We good? Does that make sense? Now, let's talk capacities. This here is your total lung capacity, TLC. So this is the total volume of the gas in your lungs. Look at me. I'm going to inhale as much air as I can. Look. The amount of air that I had at the end of this in my lungs is my total lung capacity. Now, look at me again. I'm going to do something else. I'm going to inhale as much as I can and then exhale as much as I can. Look at me. The amount of air that I just expelled out of my lungs is my vital capacity. So, vital capacity is total amount of air that you can basically operate. Are we clear? Good? Now, the total amount of air that you can inhale here is called inspiratory capacity. That's how much you can inspire, max. So you're breathing normally. Check this out. You're breathing normally. You go on the bottom of your tidal, like you normally tidally exhale, and then you inhale on top of it. That's your inspiratory capacity. And the fourth one is going to be this. It's functional reserve capacity. Why? What is the physiological importance of FRC? So imagine I am normally breathing. No effort, nothing. Are you with me so far? I'm breathing, and then something happens to me, and I stop. I stop breathing. Okay? Which means exhalation is passive, so exhaled. I'm at the bottom of my tidal volume. This is the amount of air that you have in the lungs if you suddenly stop breathing. We're good?
So when you stop breathing, you still have a little bit.
Oh, you have quite plenty.
Breathe.
You have quite plenty. If a person stops breathing, and for one reason or another, and everything else is working, there still will be gas exchange, there will be oxygen movement, there will be oxygen delivered to the, as long as heart beats, you see what I'm trying to say? It will be for some time. Does that make sense? I mean, it's highly hypothetical situation because people usually do not just stop breathing out of a sudden. Does that make sense? But in a hypothetical case, they do. This is how much air they have in the lungs. This is whatever, oxygen content, all of that kind of stuff. This is how much they have available. Are we clear? Now, a few more things, few more volumes. So, first of all, this gives us some kind of a sneak peek into why capacities, why these volumes are so important. Because this allows us to distinguish between restrictive lung disorders and obstructive disorders. So what is the difference between the two? If you think about your lungs in anatomical terms, when you think about your respiratory system, you essentially have you essentially have two types of disease. When you think about the respiratory system, you have your conducting zone and your respiratory zone. Am I clear? So in case of purely obstructive disorder, your respiratory zone is not affected. So your lungs maintain, check this out, same TLC, total lung capacity. You see what I'm saying? But the respiratory passages are very narrow. Am I clear? So example of this would be bronchitis, when your bronchi are obstructed with mucus, or asthma attack, when your bronchi are constricted. You see what I'm trying to tell you? Does that make sense? Now, the opposite of obstructive is restrictive disorder, when your respiratory passages are wide open, but the functional volume of your lung is reduced. You see that? The difference here? Can you see that? So, in the restrictive disorder, the total lung capacity or vital capacity are going to be reduced. Does that make sense? In obstructive disorder, total lung capacity or vital capacity are going to be fairly the same. But here's the question. You can't really measure total lung capacity without, like tearing a person's chest and taking lungs out. Am I clear? So how are you going to do this? How are you going to measure this? Now, I usually use an analogy of a driveway and a parking lot. So here you have two parking lots, right? This parking lot is much smaller, so you can park less cars there. Good? But the driveway here is really wide. So whatever you have in that parking lot will be moving in and out quickly. This parking lot is huge, but the driveway is really narrow. So the movement through the driveway will be the limiting factor. It will be slow. So what you can now look at these volumes. What you can realistically measure. The easiest way to measure is the vital capacity. Right? You ask someone to inhale as much as they can and then exhale as much as they can. That's your vital capacity. You can measure tidal volume. You can. Other than that, it becomes a little wonky. Okay? Now, what you can measure fairly easily in spirometry, you can measure the rate of the ventilation. For example, you can measure so-called FEV. I think it's called FEV 25. I don't remember that. So basically, FEV stands for forced expiratory volume. Now, look at this. Imagine that what I do, I give you a spirometer device, and you breathe into the tube. Are you following me? And I tell you, okay, start exhaling now, and I start my timer, okay? Or I press a button on the machine, and this machine measures how much air you expel out of your lungs in, I think it's not 25, I think it's 15. In 15 seconds, 40 minutes, okay? In 15 seconds. It doesn't really matter. Well, in 15 seconds. Now, let me ask you this. For restrictive disorder, the rate of expiration isn't going to change. The driveway is very wide. Does that make sense? People cannot get enough air because of the volume, but in terms of the rate of respiration, they're fine. Okay? Now, here, you can still expel all that air, but it will take you much longer. Does that make sense? Because your driveway, your respiratory passages are so constricted. You see what I'm saying? So, essentially, restrictive diseases affect the volume that you can get in and out. Obstructive diseases affect the rate at which you can bring air in or get it out. Are you following me?
If you had restrictive, wouldn't you just your rate of respiration would be faster?
Oh yeah. You're talking about rate of individual acts of inhaling and exhaling. Yes. When I say forced expiratory volume, and I say rate of it's not like respiration, the breathing rate, it's how fast the air gets out. Like literally, how much air you can get in a certain period of time. You can get a lot. And this is why we measure it over 15 seconds. Or even less. Sometimes I think they measure it even less than that. Like very, very short period of time to measure the width of the driveway, so to say. You following me? So the examples of obstructive will be things like asthma or chronic obstructive pulmonary disease. People with COPD basically have cystic fibrosis. It's probably both. But basically the respiratory passages are blocked. Restrictive, there are diseases. So basically what happens, check this out. Due to the fibrotic changes in the heart, you were asking scar tissue. Due to the fibrotic changes in the lung cannot inflate to the previous volume. You see what I'm saying? Emphysema contributes to this. Emphysema is an interesting disease. Check this. Emphysema is kind of both. It has an obstructive component and it has a restrictive component. Okay? We good? Questions here? Okay. Now, last sort of bit here that I would like to discuss is the idea of minute ventilation and alveolar ventilation rate. So, minute ventilation, MV. What is that? It's very similar to cardiac output. It's the amount of air that goes in and out of the lungs in 1 minute. Okay? So, it's a tidal volume multiplied by the breathing rate. So if your tidal volume is 500 milliliters and you're taking 15 breaths a minute, your minute ventilation will be 500 multiplied by 15, 7,500 milliliters per minute. Does that make sense? That's pretty straightforward. Okay? Now, for instance, how do you think your minute ventilation will change when you, I don't know, running really fast? It will significantly increase, yeah, because you're probably going to breathe faster and deeper. Okay, makes sense, right? Now, a trick question. Think about the respiratory anatomy that we just learned today. Tell me. So you inhale 500 mils of air, right? This 500 milliliters of air, percentage-wise, contain, I'm kind of rounding up, this 500 mils of air contain 100 milliliters of oxygen. Will all of that oxygen be available for the blood to pick up? In other words, out of this 500 mils, are all 500 mils go into the lungs? This is a trick question.
Wouldn't some of it go just to supply the lungs, not necessarily to, like the part, like it would go to the lungs, but just to supply the parts, not to like go to.
What's in your nasal cavity? What fills up your nasal cavity? What is right now in your nasal cavity? Air. What about pharynx? Air. Larynx, trachea, bronchi. All this conduction zone. It's filled with air. You see what I'm saying? All this air that's in your conduction zone, it doesn't participate in a gas exchange. You see what I'm saying? So with every breath, you bring some air into the gas exchange zone, into your alveoli. But some of the air that you inhale remains here. You see what I'm saying? In your conduction zone.
Does it all eventually, does it move like a...
There's not really any kind of distinction because we don't like separate, oh, these molecules go there, these molecules. What I'm trying to tell is that with every breath, out of every 500 mils, so to say, certain amount will never reach the respiratory zone. That's all. Maybe it will reach next time. Maybe some of the molecules from that will reach. It doesn't matter. Some of the air is not available. So only about 70% of what you inhale actually goes into the lungs, into the respiratory zone. The rest is used to fill up the respiratory tree. See what I'm saying? So this volume that never reaches the lungs is called dead space. Are we clear? Now, dead space can be purely anatomical, right? So we all have tracheas and larynxes and pharynges and nasal cavities, right? And also dead space can be physiological. For a second, look at this. For a second, imagine that one part of your lung, one or two segments of your lung, are so badly damaged from inhaling, I don't know, coal dust, okay? Like you were West Virginia miner, okay? Okay, so it's so badly damaged that there is no gas exchange going on. Does air still go there? Yes. Is it used? No. So this is called physiological dead space. Generally speaking, in the healthy adult, we can forget, we can neglect physiological dead space and talk about anatomical dead space. So at the end of the day, look, the actual amount of air that reaches alveoli with each breath will be tidal volume minus dead space. Are we clear? Now, how much air will go into the actual alveoli, into respiratory zone, will be determined by your breathing rate. So this is called alveolar ventilation rate. The difference between the tidal volume and dead space multiplied by the breathing rate. Are we good? Does that make sense? So these are two parameters. That's one of the exams when you will need to calculate things. I'm telling you up front, yeah, I'm going to give you numbers. You can use your calculators. So basically I'm asking you to memorize those formulas. Understand what they mean. Does that make sense to you? Okay.